that be all right if I just...
this aside here for a moment. That aside. Put it in front of him. But this, you see, we use a monitor.
Well, I don't have to see it.
No, you don't have to see it. We just put it like this. And that, there, now you can do the focus. Okay. And I'll sit fairly near the camera in hopes that then you will have more of a tendency to talk directly into the camera. That's the...
Yeah, sure.
You sure look like you used to.
Except for the hair on my head, which is practically gone.
And signs of brains.
Oh, I'm not sure of that.
I think it's all right.
You want to focus in close and then zoom? Or did you all do that?
I can't really get that. Let's see how far back.
All right. We zoom right in, so there's a little about the nose and the mouth, and then we zoom back, and it works out fine.
Oh yeah, that is good.
All right. Suppose we start it's already started, so we'd like to have this opportunity to do a videotape of you today. This is, of course, a series of trying to get a videotape record of the pioneers of science and technology who have contributed so much during the past half century. And in this videotaping, we try to keep it very informal, starting with some of your early background and some of the events which led you to the decision to take the path in life which you did with regard to your scientific and technical interests. So I think with that brief introduction, I think we would like to start. And so at this point, please proceed, Dr. Starr.
Well, let's start from the beginning. I was born and raised in Newark, New Jersey. Went to something called the Central Scientific and Manual Training High School. I knew at an early age I was going to go into engineering of one form or another. Electrical equipment and early radio construction were the kind of things which introduced me to the engineering side of the science. And when I got out of high school, I decided to go to a classic engineering school, and I went to the Rensselaer Polytechnic Institute in Troy, New York, which is still functioning as one of the major engineering schools of the country.
Yes, Rensselaer has a distinguished record of distinguished alumni.
Yes, well,
a lot of people from there.
There are more distinguished alumni coming out now, but that was in 1928 that I went there as a freshman. Matter of fact, I got out of high school too soon. Those days they wouldn't let you in until you were the age 16. So I had to work as an automobile mechanic for 6 months until I reached proper age for entry into Rensselaer. And I took electrical engineering, and in those days, electrical engineering and the other engineering curricula were very, very scheduled out. There weren't any options, there weren't any choices, there weren't any problems, except maybe getting good grades. And I worked very hard at the time. This was a period when the economics of the country was going in a state of collapse, and the Great Depression of the 1930s was just beginning. I graduated from there in 1932 and had a choice of either accepting one of the few fellowships they had for graduate work or going to work for an electric motor company where I had worked during the summers. And the electric motor company offered me one of the few jobs available, and that was very tempting. But I was very interested in the scientific aspects of engineering, the background of what made things work, and I was still very young, and my family agreed that that perhaps I could take the fellowship, which would at least support me through graduate work. And I stayed at Rensselaer on fellowships till 1935. I got a doctor's degree in physics. In those days, there were very few graduate students in the sciences, and the professors generally, everywhere, as not Rensselaer in particular, gave a lot of personal attention to the graduate students. If you had classes of 2 or 3 or 4, that was a lot. And the result was that we got person-to-person instruction from the faculty. And there was a lot of self-teaching that went on. The graduate students did a lot of work in the library, preparing their own lectures. The courses were generally run more like seminars than tutorial sessions. It was a very rewarding type of activity. I was particularly interested in the physics of solid state. So when I got my doctor's degree, it was suggested that I apply in 1935, and I applied for what was still in existence, the Charles A. Coffin Fellowships, which the General Electric Company sponsors in memory of one of their founders. And I received one of those, and I used it to study, do postdoctoral work at Harvard with P.W. Bridgman, who was the Nobel Prize winner in the high-pressure phenomena. He opened the field of high pressure, and he had a laboratory that had in it a group of postdoctorate people exploring the ramifications of high pressures. Among them, one of my colleagues in the laboratory at the time, a famous man in the whole area of engineering and the nuclear engineering developments, was Manson Benedict. Had a room just a short distance down from mine, and was doing postdoctoral work with Bridgman on the PVT diagram at high pressures for organic compounds. I was particularly interested in the metallic substances and solid state because that's what I'd been working on. And Bridgman asked me to verify some of the early experiments he'd done on electrical and thermal conductivity of materials at high pressures. And I spent 2 years with Bridgman doing that kind of thing and publishing papers in the field. This is primarily a field of experimental physics.
Did Bridgman ever get the Nobel Prize for his work in this field?
Yes, Bridgman got the Nobel Prize. As a matter of fact, I think some years before I came with him, he had opened up the whole field of high pressure phenomena by the experimental techniques that he developed.
Yes, I know. Of course, we always associate the birth of high pressure techniques with Bridgman.
Yeah.
I'd forgotten whether he ever
Yes.
was
Oh, yes.
rewarded by
He got the Nobel Prize, and he was a very good man to work with because he was an excellent experimentalist and was interested in all the areas that high pressures opened up. His personal scientific interest was in it had 2 of them. One was in the thermodynamics and crystallography, which obviously all of which are pertinent to the high pressure field. And the other was the philosophy of physics. And it was a great educational experience for me to work with him, as well as a personal opportunity to do experimental work. As I say, the scientific field in those days had a limited number of people, and you knew most of the leaders in the field after a while. At the end of my work with Bridgman, I was offered a fellowship at MIT in the field of cryogenics, and I proceeded to continue with that work at MIT. The field there was associated with the properties of solid inorganic compounds as well as other materials at very low temperatures, very high magnetic fields. And I was one of the first experimenters to use a laboratory at MIT known as the Bitter Laboratory. Professor Bitter had developed these huge water-cooled magnets powered with an old electric generator from the trolley car days to get up to fields of 100,000 Gauss or so. And I had available that laboratory and the magnets to explore the magnetic properties of materials at very low temperatures. And at that time, one had to make one's own cryogenic equipment. So I designed and built hydrogen liquefiers and helium liquefiers. Helium was a rare commodity and was measured in cubic centimeters, and that was a lot of helium. And papers both on the experimental technique for doing this came out of this work, as well as several papers on the measurements themselves in a field called paramagnetic dispersion, which is the change in magnetic properties of inorganic materials over a field of radio frequencies.
Your remark there about building your own equipment for liquid helium and so on reminds me of other people who had the necessity of building their own equipment, such that of things that we ordinarily just order out of a catalog today.
Oh, yes.
And I remember in the case of Millikan, they said he built over 1,000 lead acid cells just to get a good voltage. He built them himself, and so you've been through the same thing.
Yes, as a matter of fact, I had to give you some perspective, I had a $400 grant from the one of the philanthropic associations in Boston that Bridgman had some connections with, and I nursed that all the way through my years at MIT to buy just raw materials. I built my own electronic equipment, my old high-frequency electronic equipment, all the measuring equipment for the vacuum systems, built all the vacuum systems, did all the silver soldering, built up the whole hydrogen gas systems, the purification systems. Just everything was done by hand, and one took me a year and a half just to build the experimental equipment to run one experiment. I had the advice of other people there at MIT who worked in the cryogenic field, which was a new field for me. The physical measurements were part of my skills, but the cryogenic field were new. But Sam Collins, who was the inventor of the helium liquefier, which became a very common thing post-war, World War II, was one of my colleagues who used to advise me and help me on building this equipment. And it was a very productive period. And I was beginning to produce a good deal of experimental results in what was really a new field. Low temperatures, high magnetic fields, and temperatures at the boiling point of helium. And it's the field which is the precursor field to adiabatic demagnetization, which was a field which approaches absolute zero. And there were a group of people in the United States, the physics community and scientific community, quite interested in all of this. And the availability of that magnet laboratory was unique, so that I was able to start producing results. Well, this was fine, except that World War II was approaching. And I had published a good deal of in the experimental literature on the techniques for making measurements and techniques for building liquefiers and things of that sort. And I was approached in 1939 by the group from the Bureau of Ships, Navy Department, to come down to the David Taylor Model Basin in Carteret, Maryland, where the Navy Department has huge tanks for testing model ships, to set up an electronics research group for underwater phenomena. And as you know, the European antecedents of World War II were beginning to become very evident, and the Navy Department had brought in many of its reserve officers, professors from universities and other places, had been to build up its technical capabilities in support at that time of the British and others who were fighting the war in Europe. And they offered me what was at that time a fantastic salary. And I discussed this actually with Carl Compton, who was then president of MIT, and he wrote me several letters asking me to stay because they apparently had put me into their faculty planning. I'd been at MIT as a research associate for, I guess, 3 years, 4 years, and they were planning to put me into the faculty roster and keep me as a permanent member of the faculty, and which would have been a fine career for me. I had no great ambitions to shake up the world. I've been very happy to continue doing this scientific research because it was fun. And but the Navy Department really offered me what was then a very large amount of money, and as a civilian scientist. And I eventually succumbed to the offer. We moved down to the outskirts of Washington, Cabin John, Maryland. Had a tiny little house which we rented halfway between Washington and Carteret, David W. Taylor Model Basin, and proceeded to build up a civilian group, which was one of the first groups that the Bureau of Ships had for electronic measurements in underwater phenomena. The man in charge, who was then in uniform, who was a professor from the University of Michigan, was a man named Ormondroyd, who is now dead, but at that time was one of the leading academicians in mechanical phenomena. And one of the big problems that the Navy was concerned with was the effect of underwater explosions, mines and so on ship structures, both merchant vessels and naval ships and so forth. And the way these had been measured traditionally was with mechanical oscillographs. And that's just a big weight at the end of a pendulum, and the weight shakes and makes a mark on a tape, just like one of those little things you see that records earthquakes, except it was done with a big mechanical structure. Well, mechanical structure has a natural period which is very low, and by the time this instrument measured what was going on, a good deal of the ship's structure was already destroyed, and they knew they weren't getting the right measurements. The hope was that using electronic devices and piezoelectric crystals and so on, that they might be able to get a true picture of what was happening underwater. And so we developed and built again with a small group. I had about 15 people at that time, which I had hired through the machinery that was available, of electronic technicians principally. We developed things which in those days were fairly rare. I designed them myself, and then the technicians in the laboratory helped me build them. A DC amplifier that went from zero frequency up to several 100,000 cycles per second and was relatively flat in response. That was considered at that time a radical electronic development. We took very small tourmaline crystals and built these as pickup units. They were about the size of a dime. And then one had to get these very small signals and amplify them without distortion and so on. Well, that was part of the electronic art with which I had been very familiar. And I guess fortunate for me and my group, the equipment worked well and gave rather startling results the first time it was used to measure some of the underwater explosions, because in fact the forces were very, very high, and this was the first clear record that these things were occurring. And that work got underway. The other area that was involved was in the area of mine sweeping. The British merchant marine was losing merchant vessels for other than magnetic mines, and the underwater phenomena at the time that might be used as a triggering device was not understood. And so I set up a program at the request of the Bureau of Ships to study the underwater phenomena that might have been used involving the non-magnetic phenomena, the flow characteristics and pressure characteristics that follow a moving ship, and found that there were very many signaling devices that could be used to trigger mines, and also developed from this mine sweeping techniques, which we then tested in the model base, and then transmitted to the Bureau of Ships, and presumably have been used by the Bureau of Ships over the years.
Yes, well, I suppose at that time we were cooperating also with the British, and they were able to use some of that.
I assumed that, but I did not have any direct contact with the British. But in those days, when one developed one of these techniques, they tried it out for work that went out to the field because there wasn't any time to fool around.
At one point, the losses to mines were really staggering.
Yes, very high, and it was an odd working situation, because as a civilian with civilian people in my team of experimentalists, there was a Navy ensign assigned to us, and there were the Navy rituals, but there were civilians and civilians in uniform all throughout the Navy structure who'd been pulled in from universities and research centers, and that's really where the communication went. The formal bureaucratic communication, we don't know how it went, but the one-on-one personal contacts was the way communication really took place. And that work was progressing rather rapidly and getting to be very useful. And then I was approached by a few of my ex-colleagues in the physics field, people who had worked with me at Harvard and at MIT and so on, who got in touch with me to come out to E.O. Lawrence's lab at Berkeley, essentially to work on the Manhattan District, on the whole problem of developing separating uranium isotopes.
What year was that?
Well,
you joined E.O. Lawrence.
That was I came out in 1942 to Berkeley, and became part of E.O. Lawrence's team on the cyclotron laboratory. And he had people from all over the country, and they were recruiting people. And again, by word of mouth, as I mentioned that the scientific field was just small in comparison to what it is today. And so people knew other people. And in my case, it was about a 6 months delay while whatever machinery the Department of Defense had to convince the Navy Department that it was all right to let me go. To switch from one post to another, one had to have permission, and because at that time, as a result of the fact that I worked with the Navy, I was draft exempt, and as a matter of fact, I had volunteered to join the Signal Corps when we declared war in 1941. I and some of my associates went down to Washington to the Signal Corps to volunteer for service in the Signal Corps, and were told to go back to work, that what we were doing was a lot more important than working for the Signal Corps. Well, maybe that was true, I don't know. But because we were working for a naval establishment, we were draft exempt, and you had to have permission to go from one post to another like that. So the Manhattan District people had to do something, but they did get finally permission for me to transfer him. And I came out to Berkeley and worked with Lawrence, and that was a great experience. First, it was the first time that I wasn't on my own, where I was really under the direction of a strong leader. Because everything I'd done up to then was I had decided what to do and what to manufacture and what to experiment with and what was worthwhile doing and not. And here I was part of an enormous team of obviously very superior people, scientists and engineers of top caliber, a lot of people from industry. They had Westinghouse and General Electric people there because of the magnetic and electrical equipment, and engineer construction people and so forth. And obviously this was a big project in anybody's terms. And Lawrence himself was a real leader, both psychologically and intellectually and technically. Man of great imagination and understanding, great personal persuasiveness, dedication, and the ability to make everybody feel that the problem was a lot more important than anybody's importance. He would treat a technician in the laboratory with equal respect to a very mature scientist, and sometimes the technician was more important and more productive. And he was a man of quick decisions, too. Every morning at 8 o'clock, everybody, all the technical people in the laboratory would meet every day. And they'd have a review of what had happened the previous 24 hours in all the different experimental cells they had. And he would listen to reports, and anybody could comment. And they'd make a decision right then and there that some experiment would stop, or a new experiment would start, or they would proceed for further results, and so forth. Well, it turned out that by happenstance, that because first I'd been educated as an electrical engineer, and secondly I'd been heavily involved in material science and experimental work, that I had a sort of an intuitive background of understanding, which many of his other people did not have. Many of them were either theoretical people or scientists who'd worked in non-engineering, non-applied areas. And here he was trying to make some big equipment perform. The magnetic separators at high voltage and pushing the forefront of engineering equipment. And as a result of this, even when I first came in, they asked me to build up some instruments because that's the skills that they knew about, and that was easy. I mean, they needed precision measurements of magnetic fields and things of that sort. It was fairly routine for me. But then it was clear to me that they had other problems, and at these morning meetings, I had an opportunity to make suggestions on some of these problems. And his reaction as a leader, if it sounded good to him, and it sounded as though it was worth trying, he said, well, let's go out and get help from the machine shop and get a few technicians. Let's do it right now. Okay? And you did. You went out of that meeting and you started work on it immediately. And I did. I was lucky. The first few suggestions I made turned out marvelously well. And they had one major problem with the burnout of filaments and so on, which turned out to be a metallurgical failure. And it shows you how education pays off. I had studied the physical metallurgy from a German textbook, which had been written in the 1920s, in which one of the classic problems was the high temperature behavior of refractory metals like tungsten and tantalum and so on. And when they were describing the failure of these high temperature filaments, and I looked at one of these and it had a kind of familiar look. I looked at it under the microscope. It was exactly the picture of a certain type of failure I'd seen in this German textbook that was written in the 1920s, and I knew exactly what had to be done.
Yes, and those filaments had to carry tremendous amounts of
very
current.
high current filaments, yes.
We ordinarily think of filaments as being sort of like hair-like, and these were very big.
No, they were about an eighth of an inch in diameter. Yes, they were very big.
So burnouts of those were quite mysterious.
So I made a recommendation, which they tried out in one of the pilot units that was running, and the filament life went up by a factor of 10. And as far as Lawrence was concerned, I was the local genius, at least for that day. But as a result of the fact that I had this engineering sense of what could be done, what couldn't be done, and that my judgments had really turned out well, a special management problem came up, which got me into the peculiar spot. I'd never managed any, except for these small team efforts, any group before. The Manhattan District people, a man named Harold Fiddler, who I don't even know whether he's alive or not, was the Manhattan District representative at Berkeley, and he represented General Groves, who was heading the Manhattan District project. And Lawrence came to me one day and said that they had a big problem down at Oak Ridge, that Stone & Webster was trying to get this plant finished, get the electromagnetic plants finished, and they were getting daily recommendations from the laboratory at Berkeley to change this, to install that, to change something else, and that this just couldn't go on, that somebody had to tell them what to do and what not to do and stick with it. And they had decided that what they needed was a intermediate filter, and would I be that filter?
This must have been about in July of
around
43
around 43, right, 1943. And I said, well, fine, if that's what you want me to do, that's what I'll do. It didn't sound like a fun job. The other things have been fun. This didn't sound like a fun job, but Lawrence, I told you, was a very persuasive leader, and you had the feeling that if he wanted you to do it, you do it. You did it, and so I did, and I did that. I discovered many things about people and science, and about what goes on in the field at the same time. Many stories about that I won't mention. It's just that you learn after a while that scientists tend to get very enthused about the possibilities, whatever they're developing, and get blinded to all the things that don't work. And they have psychological biases unwittingly about these matters, and they're absolutely sure that the last thing they've done is the proper solution to everything, and that in general an individual scientist has to be really checked with his peers to find out whether in fact everything really is as clean and as strong as he says it is. And you learn a good deal of skepticism about that. You learn a good deal of skepticism about the confidence that engineers have that when they're going to build something, it's going to work. You start walking around with a big question mark in your forehead.
Yeah. Oh, that's a very important principle you just enunciated. Particularly some of these small portions of the problem, which are so important to an individual, if they're put into the system, actually have ramifications which make this thing not work, that thing not work, and so on.
Right.
So someone has to look at the whole system in order to put this in.
Yes.
So you must have had a real problem at that
Well,
stage.
I learned a lot of things out of that. In addition to a certain degree of skepticism and sort of critical comment as to make a judgment. And I had to make judgments. I had to say yes or no on things. And that's you learn how to accept gray area situations and how to exercise the criteria as to what you let happen and what you don't let happen. A very delicate matter, because in those days it wasn't just money, it was time. The time pressure was tremendous, and some of these things, when they went down Oak Ridge, meant it would be months of delay if they had to put them in. On the other hand, if the increase in performance or confidence performance would go up, maybe it's justified. And so I began to work very closely with the engineering and construction people and learned a lot about their restrictions and their decision making. That went on for about a year and a half, and then Lawrence decided that the center of activity now, because the plants were being built, the so-called alpha and beta buildings, the stages at Oak Ridge were being built, that the center of activity for further improvement development work ought to be in Oak Ridge. And they asked me then to leave Berkeley and to go down Oak Ridge to run what was called the Beta Pilot Plant. And I did that, and I guess that was in '44, and that was an interesting experience too, because I had a large number of these so-called beta cells in that building, and we had 7-day, 24-hour operations, and most of the staff had been engineers that had been drafted by the Corps of Engineers and assigned to Oak Ridge, and but they were good people, and I had a regular ritual of walking around each experiment, looking at the results, and deciding then and there whether what should be changed or what should be shut off, what was being promising, what was unsuccessful, and after a while you get a sense of judgment as to that when something, even though it's imperfect, shows promise, and when something which looked good isn't good, and a sense of what to try and what to change. And quite literally, there weren't any committees, there weren't anybody leaning over our shoulders. The whole group doing experimental work had ideas at which they were free to try, and I had very, very good people, working on all kinds of the problems that came from the failures of the equipment, inadequacies of the equipment, so on.
I was going to mention there, and perhaps you may have some comment on it, that these very excellent people apparently came out of some sifting process from the Army and appeared in very short order, it seemed, and yet all of them had really superior ability, and it was one of the most striking examples of being able to recruit an awful lot of good people in a hurry. And I was wondering if you had any other feeling on that.
I don't know how the Corps of Engineers did it, but they were surprisingly good. They apparently were the recent graduates. Most of them were graduates from the major engineering schools, and I'd say in general what it means is that the graduates of good engineering schools under the right circumstances can be productive. And I think a lot depends on the environment. First, you learn a lot about motivation of technical people. There are two things. One, they have to feel that what they're doing is worthwhile. There has to be a sense of commitment. And the second is they have to have the feeling that they're being given an open-ended opportunity to make a contribution. And this makes every individual stretch. There's a target he's shooting for, and he's free to contribute as much as he's capable of. So every one of them puts out. And what happens in that is that some people are better than others, but they're all pretty good. In any event, that went on. I used to go through all the production buildings, talk to the supervisors, and suggest changes in the actual production protocols, at what level they operated different parts of the equipment, for how long, and so on. And also listen to some of the problems to see if there were changes we could make or problems we should look at. One of the big problems in those days was the failure of electrical insulators. At these high voltage, they used to get completely coated with the uranium compounds and decomposition products, and they would fail on the surface. And to show you how some of these things work, we tried everything in the experimental facility, all kinds of arrangements, and the fact that the results seemed mysterious bothered me individually. So I sat down with one of the young people working with me, and I worked out what was happening in the electric field around the insulator just with a pencil and paper at my desk as the insulator got coated with material, and worked out a way to shield the insulators that was very unusual, and for which there was a Manhattan District patent, which is still there somewhere, to protect the insulators. And we tried it out in a power plant, it worked. Then we tried it out on a big scale in one of the operating plants, and it worked. The insulator failures stopped. And that was an application really of just scientific analysis to an engineering problem, which is one of the other extremes. And sometimes you can sit down with a pencil and paper and figure out what was happening. It's like the story of, as a diversion, the story of Eugene Wigner and the Hanford reactors when they stopped.
Oh, yeah.
You can sit down with a pencil and paper and figure out what must have gone wrong. And that's what happened here.
And of course, there's an extremely important thing to solve, too, because when the insulators go, you get no more production.
Well, the production went down. In addition to which, we were running out of raw material for the insulators. The Coors Company was the big supplier at the time. They couldn't make beers, so they were making ceramic insulators, and they just had limited production. And this was getting to be one of the issues. Well, that was also an education to me. It gave me confidence in the ability of the human mind to solve problems, as well as working in the laboratory and the pilot unit gives you the confidence that hands-on effort will also pay off. And there's room for both. But when things keep reoccurring in the laboratory in a mysterious way, maybe it's worthwhile to go back and begin to think. And I think that's what happened there. In any event, that went on until the end of the war, because our job at that time was to make enough separated uranium for the first weapons tests. And as you know, the electromagnetic process did for the initial enriched uranium work for the weapons testing and the first weapon. And then when the war came to an end, I was still doing that, but I was then sort of freed to the pressure was off. And at that time, General Groves appointed this Manhattan District Committee to examine the whole capability of monitoring the whole weapons business to see whether one could control and monitor weapons manufacture around the world. And there was this was a committee which was then reported to the Oppenheimer-Baruch group that was then making that national policy of what to do internationally.
That was about the initial non-proliferation
right.
work.
That's exactly right.
That's gone on ever since.
And on that committee were famous people that I represented the electromagnetic plant. Manson Benedict represented the gas diffusion process, and there were people from Los Alamos, people from the isotope business, people from the weapons laboratories and so forth, and from Hanford and from other places. And we were chauffeured around with one of General Groves' deputies. I've forgotten his name now, a very impatient man from the Corps of Engineers, looked upon all the scientists as long hairs. I remember Frank Spedding, the isotope man, was on that committee. And Frank Spedding was a very, not petulant exactly, but he wanted all kinds of little things done. And he wanted to be met here, and he wanted this on his diet, and he didn't want to stay here, and so on. And I could just see our Manhattan District custodian burning between the ears on these things. But it was a very interesting thing. We came out with a very thick report, which I believe is now declassified, but it laid out specifically what you could and could not do if you wanted to go into the weapons business on a small scale and a big scale, what you could and could not detect, and how easy it would be to control it internationally. That information was then given in informal briefings to Oppenheimer and his committee, and that presumably was a technical backup for Baruch's plan, which he then proposed to the United Nations, you remember, which I think would have been a marvelous step, but which the Russians turned down, the USSR turned it down.
Yes, that was totally turned down,
Yeah.
but in retrospect, that would have been the chance for the whole world.
Right, yeah, because it would have essentially moved the whole thing into a non-military phase on a worldwide basis. And I think that it's very unfortunate, as a matter of history, that it wasn't accepted. But in any event, that introduced me to the total picture of what had been going on during the war, of which I'd only heard fractions. And I got very interested in the nuclear reactor, which seemed to me a fascinating opportunity for really a new energy source. So the post-war theme, which many of us got involved in, was the opportunity to convert all of this new technology into a new energy source for the world. A theme, incidentally, which I still has great merit in my mind. And so I asked to be transferred to the Clinton Laboratories, which was the nuclear reactor activity at Oak Ridge. And I just moved down there, went to work, and spent about 6 months tapping everybody else's brains, reading all the literature, catching up with the theory. I even wrote a paper on the theoretical calculations of what went on in nuclear reactors, looked at the engineering experimental things, and became part of the senior development team at the Clinton Laboratories. That was, the war was over by that time, and there was a big debate going on, as you may well remember, on the who stays at Oak Ridge and who would leave, and it was a real attempt to get many of the people who'd come in for the military purposes during the war to stay, because so that Oak Ridge would be a continuing R&D center. And this was a matter of some thought by all of us. We were also at that time involved in the political side.
Yes, the civilian versus military control.
Right. There was one act, I forgot, what was it, the May Act or something like
May
that?
Johnson Act.
The May Johnson Act that was going to put it into the military, and then there was a McMahon Act that was going to turn it into a civilian. And many of us felt at that time that as part of this mission of a civilian energy source, that this ought to be under civilian control. And so we were trooping back and forth to Washington, and I was one of those trooping back and forth to Washington and holding meetings in Oak Ridge on what we ought to be doing. So that took some time and some energy. They were all very cheered when the McMahon succeeded in getting his act passed. I'm not sure we fully realized the portentous nature of what we were doing. These were sort of almost simplistic concepts on our part. And I'm not sure any of us were sufficiently sophisticated politically to thoroughly understand all the ramifications of what we were suggesting. But we went ahead and did it and felt very successful about this.
I remember I interviewed Chet Hollifield on this subject here recently, and he was very thankful for the way the scientists rallied back of this and made it possible to turn around.
Yes, well, as a matter of fact, that's how I first got acquainted with Chet Hollifield, and for reasons of, I guess, of personality as much as anything else, we hit it off immediately. Here was this congressman who had no formal education at all, self-made congressman, and here was I, gone through all the litany of these universities and so on, and we just hit it off immediately. And I've always had great admiration for him. We always got along very well. And I think one of the key elements, it's just a side issue, was the element of personal integrity. I think he felt that I was telling him the truth as best I saw it. I wasn't playing any games with him. And I had the feeling that he wasn't playing politics with me, that he was this matter of confidence in his integrity and his confidence in me as not leading him down some primrose path. I think that may have been the common bond. I had just supreme confidence that Chet was telling me the truth. And I think he may have had that same feeling about me. But in any event, we got along splendidly and did for decades after that. But this was a fairly exciting period, but also a period of instability in terms of personal planning. And about that time, at the end of, I guess this was the end of 46, early 47, some of the people who had worked with me during the war at Oak Ridge got in touch with me. They'd been out in California and they had gone into the aerospace side and asked me if I would want to come back to work on the application of nuclear power to aerospace vehicles, an international continental ballistic missile, and so on. And both my wife and I had gotten fond of California during our stay in Berkeley. It's a state with great varieties. You can live anywhere quite happily, but we got very fond of the variety and lifestyles in California, and we thought it'd be nice to get back. So I went to work. I decided to leave Oak Ridge, and I went to work for North American Aviation in Los Angeles on what was for me a temporary job. I thought it was a good idea to go there. we get our feet in California. I'm not sure I'd have that same courage today, but I was young, and we only had one small child at the time, and I felt we could do anything. And so I did. I came back to Los Angeles, built up a group of what was called the Aerophysics Laboratory at the time. And the object of that laboratory was to look at all the alternative ways of moving intercontinental ballistic missiles. And so there were these few people that had worked with me at Oak Ridge, and I recruited a few more. This was a conventional aerospace company, and we were sort of an unconventional group. But by that time, I had learned how to manage managements, and got my experience in Oak Ridge. And when we needed certain freedoms and untraditional working areas and so forth, I just went out and got them. Because we did both experimental and analytical work, and we came out with a very big book, which is a sort of an unknown classic, because it was classified for almost 20 years. It's been declassified now, which described how you built nuclear rockets and nuclear ramjets, and had in it all the experimental work on the materials. Carbon elements embedded with enriched uranium, coated with hydrogen-resistant coatings, all of which we had done in the laboratory at North American. Beryllium oxide fuel elements for use with air, for ramjets. And we actually designed all the equipment and tested all these key fuel material things, and came to the conclusion at the end of 2 years that one, it was feasible to build both of these. Secondly, that from the point of view of an intercontinental ballistic missile, the chemical rocket was much better. And I went to the North American management. I remember my meeting with the chairman of the board and the president of North American, both of whom were engineers, and saying, I think we ought to tell the Air Force that we'll write all this up, but that they shouldn't spend any more money on it. And they were first shocked because it's untraditional to turn down a government program, and secondly, it's untraditional for people to talk themselves out of a job.
Yes. Incidentally, what year was that?
Well, that was in 1948 or 9.
Oh, yeah. Very early.
Yeah, very early, because now I've got the unclassified report back on my shelves. Glenn Seaborg got it declassified for me when he was chairman, because it's been sitting there classified for decades. That report became, just a side issue, became the precursor for Los Alamos on the project NERVA, which was the nuclear rocket that was going to go out into space. At that time, there wasn't any space mission. It was only the intercontinental delivery for a weapon. And it also became the precursor of Project Pluto, which was the project for a nuclear ramjet.
Yeah.
And both that report was the takeoff point, and they used exactly these materials that we had developed, and that's the reason the report was kept classified for so long. And I was asked that by the management of North American. They finally agreed that because I said there's no point in our fooling with this anymore, and if we continue to work on this, we'll be spending money under false pretense as far as the Air Force is concerned. And so they sent me to Washington to discuss all this with the Air Force Directorate of Research and so forth, who I think were fairly reluctant to see these projects terminated. But I was fairly stubborn about it, in the sense as far as I was concerned. It wasn't the thing to do. And And when I came back, we reviewed the whole thing. Kindleberger, who was the chairman of the board, said to me, "What are you going to do?" And I said, "Well, I'm going to go out and look for a job." I'd been with them for 2 years and had built up this group. And he said, "What do you want to do?" And I said, "Well, I'd like to work on the civilian uses of atomic power. I think there's a future for that, and I think it's important." And they said, "Well, we as a company have thought that we ought to have some non-military work. All their work was military. Would you be willing to stay and we'll support your group?" We had 15 people to see if you get your feet on the ground. And I said, "Well, I hadn't thought of that. But if you're willing to try it, I'm willing to try it." They said, "Well, you go ahead." So they set me up as an independent department. And I then went back to Washington and told the people in the AEC that I was cutting out this military program. I wanted to go into the civilian group. And much to my surprise, I guess Hafstad was still director, of the...
Oh, yes, Larry Hafstad,
yeah.
and this must have been about 1952 or
Yeah,
thereabouts.
yeah. Well, so it was before that time, but just a year or two before that, and Hafstad said, "Well, gee, this sounds awfully good. You've got a very good group. I've looked at the report. That's great work. We'll give you a contract." And I said, "Well, how can you?" They had just made a decision, you may recall, to turn all civilian reactor work over to the Argonne National Laboratory.
Yes, that was
And they had just made that decision a few weeks before.
It was a big decision.
I know. And Oak Ridge was supposed to drop reactor work and so forth, and civilian power is going to be at Argonne. And Hafstad said, "Well, we can't really cut out people who are competent." And he said, "I'll tell the Chicago operations office to give you a contract." And I remember distinctly what happened. The Chicago operations office got up on its high horse and said, "We've got orders, everything's going to go through Argonne. You can't have a contract." And there was a meeting in Washington, and Wally Zinn was there, came up to me and he said, "Look," he said, "I don't care if you work on this or not." He said, "I just like to do what I want to do, and you can do what you want to do. Let's go tell these people that no more argument, that you can have a contract." So we both walked back to the meeting, and I've forgotten the name of the man of Italian extraction who was the head of Chicago operations office, Al Tamaro.
Oh, yes.
Al Tamaro. And Al Tamaro was being, a hard-nosed field officer, and he'd had his directions from Washington. Unless they were changed by the commission, he wasn't going to change anything. We both walked in and we told Al Tamaro that we had decided that there wasn't going to be any more argument about it. And he looked at us and said, "Okay, I give up." And so we got it was a matter of a month or two after I decided to cut off the military work, I got a contract to work on the civilian side.
Well, that's a very interesting story. Yeah. I don't think that story is really clearly told.
Yeah. Well, in those days, of course, the sense of mission inside the AEC was very strong.
Oh, yeah.
A sense of national destiny, if you wish, that getting the job done and really doing something for the country was a lot more important than the paperwork. I could always get my way through the AEC by just talking about what we tried to do rather than arguing about the paper ritual, because the AEC could always find a way through the ritual if they wanted to. And that feeling, as you know, was very strong, in this, particularly in the early days of the AEC, before all the bureaucracies built up.
Yes, of course, but at that time with people like Hafstad and Fisk, who had real experience and had a broad vision, and this was much easier. Yeah, that's right. And not only that, but they had confidence in people. I might say that I got very good friends with Al Tamaro after that, because again, I want to keep harping on this theme. One of the things you learn with people who have responsibilities and accountabilities, that
they need people around them whom they can trust. This matter of personal integrity, both technical and personal, is a very, very important thing. And if people feel that they're working with someone who isn't playing games with them or trying to squeeze everything out of any arrangement for their own benefit, that feeling of confidence builds up a good working relationship. And we developed a very good one with the Chicago operations office and with Tamarone. So to the point where I could call him on the phone and say, Al, I need this and this and this, and he'd get it arranged immediately. Because he knew if I needed it, it was something worthwhile doing. And but in any event, we became, our group then had official AEC support. We changed the name to Atomics International as a group, and we started working on a variety of things which we had proposed to the AEC. They just mentioned a few of them. We developed our first job was to look at a way of designing reactors to increase the production of neutrons for either tritium or plutonium, and that was a competition. I had picked the heavy water, natural uranium. Wally Zinn had picked the pressurized water system with enriched uranium, convert enriched uranium to neutrons, and we had examined. We ran an analysis and did an engineering study, and he ran one. And then there was a big review in Washington, and it was decided that the heavy water approach, which we had chosen and the approach we'd taken, was the right one, which we felt very good about it. But then they turned the whole job over to DuPont, which is where Savannah River came in. And I think they felt quite properly that we weren't structured to handle anything as big as that. But in any event, our next task was to work on the fast breeder. And out of that program came the Hallam plant, which was a thermal spectrum sodium-cooled machine. And we developed the first big liquid sodium equipment anywhere in the world. And that's the origin, the Liquid Metal Engineering Center down in Santa Susana. And we built the sodium reactor experiment, which was the first little reactor to produce electricity on a power system. I think it was something like 10 kilowatts or something of electricity, but it was connected to a steam turbine and generator, which went on the Southern California Edison line. And we have a picture somewhere of Admiral Strauss throwing the switch to put the thing on the line, big grin on his face.
Let's see. What was the date of that?
Well, I'd have to look it up.
I think the EBR-1 also made some electricity later on, about a year later.
No, EBR-1 lit an electric light bulb, and it may have done it before we did it, but it was not connected to a utility grid. Ours was connected to a utility grid.
Connected to a grid.
And if you want the date, I can look it up.
No, it's just a matter that those were
sometime in the 1950s.
Yes.
And that reactor was just dismantled a few years ago. It worked beautifully, and that became a model for the Hallam plant, which was an 80,000 kilowatt station in Hallam, Nebraska. And we went on to engineer that and build that. That ran for about a year, and then it failed through leakage from thin stainless containers into a graphite body, leakage of the sodium. And it took us a while to figure out what was happening. It was a design defect in the expansion and contraction of these protective films of stainless steel. By that time, the commission had dedicated itself to the fast reactor program only. That was in 1964 or so. And if you recall, that was a period in which all reactors of experimental nature were shut down. Oak Ridge reactors, the experimental gas cool was mothballed and so on.
Yes.
And now one of the other reactors so that program came to an end. Another reactor which we developed during the 1950s was the organic moderated reactor. And we built what's something you couldn't do today under any circumstances. We built the first experimental organic cooled moderated experiment to show that the system would work in Idaho in about a year and a half with a very small budget of money, and did it fast with just the approval of the division in Washington. Said go ahead, and that was it. That was all the approval. And we dug a hole in the ground in Idaho, built a reactor in it, and used the earth around it to shield it. No containment building, just a shed to keep the rain off. That ran for a year and 2 years to prove out the fact that the organic liquid could be used for this purpose.
Yeah, there was a problem there of stability of under radiation.
Yes, the organic decomposes under radiation.
And there was no way to find that out except to do what you just did.
Right. And as a result of that, we built the Piqua organic cooled moderated reactor in Piqua, Ohio, which was a small station in the middle of the town of Piqua, which ran for 5 years successfully, gave no trouble, and then was stopped simply because the AEC didn't want to support it anymore. It also became the precursor to a joint experiment with joint design with the Canadians as a follow-on to the CANDU reactor, which is a very expensive installation. To lower the cost, they wanted to use, instead of high-pressure heavy water, they wanted to use the low-pressure organic. And so the Canadians, jointly with Atomics International and with Combustion Engineering, where Wally Zinn was, we designed a full-scale power station, heavy water moderated organic cooled, which was ready for construction by the early 1960s. It was in the budget and everything else. And the Canadians were going to use this as a model for the next phase of the CANDU reactors. They had an experimental station built at White Shell in Canada, which is still operating, which is run on organic as a test reactor, still running. And that whole program came to an end. As a matter of fact, the way that was done is Wally Zinn and I set up a special project. He and I were the two directors of the project. And a man named Chuck Storrs, who became chief engineer at Combustion, was the man who was the principal designer. And we were ready to go ahead and build this full-scale station, I guess, with 300 or 400 megawatts, something of that sort. And that came to a halt all at the same period. The third thing we did was the SNAP program, the getting a nuclear power into space. And that was the complete opposite spectrum, a very, very small reactor to produce tens and hundreds of kilowatts, which would be launched by a rocket and then become a power source in space. And that was a very exciting development, because you had to shrink the reactor down, and you had to start it up after it was launched, and it had to be self-stabilizing, all kinds of characteristics. That was
and then operated in outer space.
Yes, operated in outer space. And in fact, that was one of the most exciting technical developments in the nuclear field that we've ever undertaken. And the group, by that time I had about 3,000 people at Atomics International. What with the liquid metal center, the organic cooled reactor, the sodium cooled power reactor, and this space nuclear applications, the SNAP 10A. And that was a fairly exciting venture technically, with a lot of original new developments. And we developed new fuel. All kinds of things were done. And it was really the borderline of engineering technology, materials technology, and science all brought together. And it was launched in 1965 from Vandenberg and operated for about, I think, 40 days or something of that sort. And it stopped operating, having nothing to do with the nuclear power development. The DC electricity coming out of thermocouples was supposed to be controlled by a voltage controller supplied by NASA, which and if the voltage was too high, then the adjustment went back and reduced the reactor power. If it was too low, it raised it, and so on. And that piece of equipment failed. The signal came back. We had instruments on everything, and the signal came back that the voltage controller had failed. And so the reactor shut down. It's still up in space, and one of the fascinating things would be now, it's almost 20 years, it would be wonderful if someone with one of these space vehicles could get up and see if they could start it again.
Yes, but, that's amazing. That was the generation of electricity was from thermoelectric.
From thermoelectric couples, right. And but that was an exciting venture. Now, incidentally, at that time, if you recall that period of the 1960s, we were fairly open with the rest of the world and the Russians on the because of the Atoms for Peace program on all these technologies, and the Russians were trying to catch up with us on the space applications. They showed us their models and so on, and they were always, I'd say, 3 or 4 years behind us. They've continued. Their program has continued to this day. They've launched several nuclear-powered space sources.
Do you use a thermoelectric generation?
They use that. They've been playing with thermionics. There are several converters, and that program came to an end for an odd reason. Showing what the difference between near-time and long-term perspectives will do. The work on that was classified, and eventually it was supposed that the military would use this power in space. Chet Hollifield had a closed meeting with the military and the AEC to see what continued interest would be for continued funding of further development. And I had written to Hollifield and put on the record the fact that one could foresee large applications of electrical energy in space for communication purposes, for radar, for all kinds of devices, observation devices. And I said at the time that one of the limitations of space instruments and vehicles was the amount of electrical energy available, and that and I felt this would open up a whole new horizon for space development of equipment and ought to be continued. Well, they had the hearing, and what really had happened was that there was a big argument as to whose budget this would go into. The argument was that if the Air Force said they had future use for this, they would have to take money out of their budget and give it to the AEC. And the AEC wasn't going to go out and make a decision that the Air Force needed it. So the Air Force came in and said they had no foreseeable need. And that killed that project. Now, as you may know, if you read the literature, the DOD has come back and said, gee, we need all kinds of electric power in space for all kinds of advanced uses, and how are we going to get it? And so 15 years have gone by where we could have really been developing things, and I think that what happened was, and this happens often in national, particularly at this level, a bureaucratic short-term conflict resulted in a cancellation of a long-term worthwhile development.
Yes, well, we speak glibly today of things like Star Wars and things like that, and we have no real reliable power source, I don't think, for this.
Well, we'll be able to get it, but now we have to catch up. Not only is momentum lost, but there is a certain learning that technical people go through when they try things and fail. And that learning is lost when someone new steps in. So we're going to have to pay again for the costly education of a new generation of people. Oh, they'll get there eventually. Good people can do these things, but it isn't going to be inexpensive, and it just was unwise to drop this. Well, those are the kind of things that Atomics International did, and it played a role in the fast fuel test facility, and that was a very exciting period. At the end of 1965, the Air Force, the AEC, as I said, had changed course, as you know, during 64, 65, was concentrating its budget, narrowing down its expenditures, and they wanted everything focused on the fast reactor and on the fast fuel test facility, principally. And I guess I personally felt that a lot of the excitement and also a lot of the mission of the AEC had lost its intensity, I guess, that more than anything else, that too much of the operation had become one of keeping teams of people alive, keeping them going, and finding funding to keep them going, and not enough of an exciting mission. The sense of accomplishment was getting diminished, and at that time I had been an advisor to the School of Engineering at UCLA for many years. Their dean died, and they were looking for a dean, and they'd spent 2 years looking for one and hadn't found one. And the chancellor of the university came to me and said, could I possibly be interested in taking on a task as dean? I've been 20 years with North American, and Rockwell was at that time beginning to take over. So it's become Rockwell International. And the management wanted me to stay. They had very good relations with my bosses, and I had really a fine spot. And if I'd been willing to coast along in sort of a benign environment, there would never been any question. But I just felt the element of excitement, the fun part of engineering was missing. I think that's another thing that I've learned, that everybody has to make a living, and you've got to eat and raise a family and all that kind of things. But the real fun comes from a sense of accomplishment. I find engineering and technical challenges exciting. It's like I go mountain climbing and things of that sort, and it's a challenge, a sense of accomplishment. For me, that's fun. And just working, all activities have certain chores you have to do, but the chores are part of the game of getting something done. But if the end accomplishment has lost its attractiveness, then for me it wasn't exciting. So I decided then to leave North American. So the temporary job I took with them turned out to be a 20-year commitment.
Yes.
And I became Dean of Engineering at UCLA. That was a completely different environment. It was both interesting and frustrating. For the first time, I found that there is the element of leadership in the university doesn't play the same role as it does anywhere else. Faculty aren't don't have the same commitments, don't have the same willingness to work on a team basis. You're dealing with a bunch of individuals who tend to use the university as a hotel, if you wish, to live in and to do their thing. And so you're dealing in a university with a bunch of individualists, each one of them with a different set of objectives, and getting things done to improve the quality of performance or change direction can be done, but it can be done only slowly. At UCLA, as dean, I worked very closely with the other deans, and we did get things done, but they're very, very slow. One of the men that I worked very closely with, who was one of the people I'm sure that will show up in your records, was Bill Libby.
Oh, yes.
Who was a senior professor of chemistry there, and who had always a very imaginative guy. And we set up a curriculum, a new graduates curriculum in environmental science and engineering, the sort of thing that in industry I could have gotten through in a month or two. It took 3 years at the university to get approval for the new degree. The committees, endless committees and approvals and so on. It's just a slow-moving institution. I set up a joint with the medical school, an Institute of Engineering Medicine, which is functioning now, but it took 5 years to get that going. I found a man a very excellent man, with $10 million to give to the university to create such an institute, worked it out with the medical school, and got that institute going. It's now functioning down there. I got some new faculty, people who had fresh approaches and so on. But it just took a lot of time to get small things done. Well, the improvements were of the marginal nature, and if you want to do anything very substantial, it just took a lot of effort.
Yes, my son, incidentally, is now doing graduate work at UCLA Engineering, so he loves it very much.
Yeah, it's a good school. It's a good school. And I would still be there because I was spending about a quarter of my time with the National Academy of Engineering, getting that moving, and I became vice president of the National Academy of Engineering. And I had the choice when the first president left of continuing past becoming president of the National Academy of Engineering, and I decided I didn't want to do that for various reasons. I had a special interest in an area that I had developed I guess because of all the fact the university is slow moving, it also gave me time to do things that I was interested in on a personal basis. And so I had started some work in an area which is now called risk analysis. And I had a group of graduate students who worked with me, and in 1969 published what has now turned out to be a seminal paper in the field, the first quantitative analysis of social risk-taking on a big scale.
That's a rather classical paper, as I remember.
Yes, it is, and it was the first time anybody had ever tried to quantify the benefits and risks of large technical systems and how society has handled these in a quantitative sense, based upon a quantitative empirical data. And that turned out to be, this is still my major personal interest, and that turned out to be a fascinating subject. It all started in my attempt. It came out of a discussion I had with Glenn Seaborg, in which I had urged the AEC that it could not constantly say that nuclear power was safe to the public, and try to give the impression that it was absolutely safe. And I said that's unrealistic. Sooner or later, you're going to get caught into having to explain it to the public, and you cannot prove absolute safety. And what you've got to show is where it fits in the spectrum of public risk-taking. And I remember giving a preliminary briefing on this to Seaborg and other people in the commission, and his coming up to me at the end of an hour-and-a-half briefing and saying, He said, that's fascinating. He said, that's the best explanation of the whole risk situation I've ever heard. And I said, well, you going to use it? He said, no. He said, I can't get up in public and say that there's any risk associated with nuclear power. And I said, well, you're making a mistake. But I couldn't convince him. But I decided then that one had to do these things. One had to make this kind of a study. You had to make, you had to legitimize the status of public for public acceptance, and I got a positive response later from Jim Schlesinger when he became chairman, because he came in and he'd heard about this briefing and asked me to come to see him, and I told him about it, and I said, you ought to sponsor a study in detail to flesh out what I have given you in a superficial thing and in a superficial way. And I remember saying, well, he said, let's go down and have lunch. And he went down with me to some Chinese restaurant nearby. And over lunch, he made the decision, to start what was the Rasmussen report. And they originally asked Manson Benedict to head it. Mm-hmm. And Manson felt he was too busy and suggested Norm Rasmussen, who hadn't been involved in any of this at all.
Oh, yeah. But became very enthusiastic.
Yes. And that's how the Rasmussen study got started. But in the meanwhile, I was pursuing this work, and I was also very interested in the whole energy picture, which is also one of my interests. I have always felt that energy was one of the prime ingredients to civilization, and more than just superficially. That energy was just not another commodity like potatoes or beans, and that there are no substitutes for it. And that it played a key role, and that electricity played a key role. And I was giving a series of lectures down, I think it was at Georgia Tech, some symposium or other, and one of the utility executives who was on the panel came up to me afterwards and said, he said, the industry's been talking about setting up a research institute. Would you be at all interested? And I said, no, I'm very happy where I am, but I said, if you're going to do something like that, let me write you a letter what you ought to do. And I wrote him a 6-page letter. That was in the beginning of 1972. And I wrote
that's about the time you wrote that classical publication in the Scientific American.
Right, on energy, yes. And I wrote him this letter that said, if the electric utility industry is going to research on a national scale, this is what your program ought to be, this is what your philosophy ought to be, and this is how you ought to run it. And it's a very extensive letter, and I sent him the letter, and I didn't hear from him for months. And then in September, that was, I think, back in March or something of 72, in September of 72, I got a telephone call from one of the local utility executives in Los Angeles. Said we have a search committee working to find somebody to head this institute we're proposing, and he said we would like to consider you as a candidate. And I said, I'm not really very interested, and I said, I'm arranging to take a sabbatical. I was going to go to write my book on risk analysis at the University of Sussex in England, and I said, I'm not very interested, but he said, well, will you talk to us? And I said, sure. And so we had a meeting, and I told him the meeting started as a breakfast meeting at 8:30 and it lasted till 12:30. And there were about 5 of them, and except for I knew about half the group from other activities. And I found that this may be interesting, a piece of history, because I found out that they start to ask me questions about how much experience I had as an administrator in doing this. And I said, let's not waste time on that at all. This is just at the beginning of the breakfast. I said, let's not waste time on that at all. I said, I'm a professional research manager, and said, don't bother asking those questions. I said, when you go in to have your appendix out, you don't go ask the surgeon. There's a long history. He's either a professional or he isn't. If he's a professional, he's going to do a good job. I said, that's not the issue. I said, let me ask you some questions. I said, what is it you want this institute to do? And we had a 3-hour argument about it. And they had a fairly, or started off with a fairly conventional view of what this research institute was going to be, marginal improvements in transformers and figuring out why fuses weren't reliable and things of that sort. And they were really talking about a test laboratory. And I explained to them that that's not what they needed. They need something of very broad scope to get back to the fundamental issues that are going to determine their future. And we had about a 3-hour discussion in which essentially I was putting them through the catechism, if you wish. And I was sure that I annoyed them terribly. And that was in September. And I came back from that, and I told Doris, I told my wife, I said, it was a very interesting morning. I said, I'm not too interested in the job anyway, because they'd never give it to me under my terms. And I said, by the time I got through with them, I'm sure they didn't want to see any more of me. I didn't hear anything from them at all until the middle of December. And I made all arrangements to start my sabbatical in January and so forth. So I get this telephone call from this local man on the search committee. He said, I'd like to come up and talk to you. He said, our committee has decided that you're the man that ought to have this job. And I said, gosh, I don't know if I even want it. I said, it has to be on my terms. He said, let me come up and talk to you. And he did. He came up. He was the president of Southern California Edison at the time. And he came up and said, look, he said, we think you know more about what we need than we do, and that we'll give you a free hand. You can set everything you want. And I went to see Dave Saxon, who was then the vice chancellor at UCLA and became president of UC, good personal friend, and we discussed it. And I said, if I can really play with this for 5 years and no one's going to interfere, I can have a real fun game out of this. On the other hand, I said, I don't want to leave you in the lurch. And we discussed it, and we decided that if I wanted to do it, I should do it, and that we'd phase out my engineering and so on. So I agreed, and on the basis of just their word, no contract or anything, but I made it very clear that I was going to run the show. And it sounded very arrogant, and that's why I didn't expect to get it. I became officially the president of the Electric Power Research Institute, which they'd set up as a Delaware corporation in the middle of '72. That's the only thing I didn't have any control over was the name. On January 1 of '73, one of the graduate students working with me, who's here now as a vice president, insisted on coming with me, and my secretary. And I got a little office in Los Angeles. That was our office. I had over $60 million in the bank.
That was a good start.
And a lot of people from the industry calling me up on the phone telling me what to do, and I very politely tried to turn them off. I decided what ought to be done, and I called up people around the country who I knew were the best people in different areas of fundamental technology. I got the man who was my chief administrator at North American. I got him to transfer to come work with me as chief administrator. We went out on a hunt for a place to settle down. We got this place. I bought this place in 15 minutes. Didn't have to ask for anybody's approval. iTech was here originally. They built the building. They'd run into financial troubles. They decided to condense their activities into San Jose, and then they moved back to Boston. The building was empty. I got my administrator had been here and decided that it was all right physically, and I came up. We decided what the proper value was for the property, and we got the vice president from iTech here, and it was fairly straightforward. I said, we'd like to buy the building, and he said, well, fine, and I said, I don't know what you're asking for. What are you asking? And I said, he gave me a number, and I said, well, that's completely out. If you want to sell the building, I'll give you the price right now, and you can get it at that price. And I gave him the price. It was a fair price. We had studied the real estate values and knew exactly what the building was worth. And I said, I'm not going to give you any more than that, and either take it or don't. And he said, let me call head office, and he did, and he came back a few minutes later and says, okay, it's a deal.
Well, that's getting a thing done fast.
Yeah, and
perfect location.
Yeah, well, it turned and we had already had a study made and so on as to what we needed and so forth. And so by the middle of the year, we were located here. I had by that time about 40 people coming in, some already on the payroll. By the end of the year, we were up to over 100, and within a matter of a year and a half, we were going full blast. And during this period, I was already giving out contracts on areas which I knew the industry needed, and I didn't need any advice on those things, and got things going. And I remember the first board meeting, before the first board meeting, I'd already had a press interview. I'd already appeared before a congressional committee, to the Senate Commerce Committee, to tell them what the program was. I'd laid out the whole program, the philosophy, what we're trying to do. And then I appeared at the first board meeting, after having committed everybody to everything. And,
right, yes, well, that's the only way, I guess, you can get into operation fast.
Well, it worked. And I lucked out, I think, primarily because of the choice of people that I had. They're just marvelous guys. There are a lot of good people in the country, and these were among the best. And they felt that we were getting things done. And they've all had a reasonably free hand. And as a result, from the point of view of the utility industry, we have been a marvelously successful investment. And the institute now has a reputation which is worldwide. Our relationships are worldwide. And it's really has been a very fun thing.
Very, very successful thing, and to be started out.
And I'll end the story by where I am now. A few years ago, I decided that the place was running beautifully, and I'd had enough of salary reviews and budget reviews and things of that sort. And we went out to recruit a president to take my place. We got Floyd Culler from Oak Ridge, who I'd known for 30 years.
A very wise choice.
And who was remarkably fertile brain, and the board created a special post for me. As I'm a consultant at EPRI, but it's more or less full time. I'm a vice chairman. The board of directors has two vice chairmen. One rotates year by year as utility executive, and I'm a permanent vice chairman. And I have a group here called the Energy Study Center. It has about 6 very senior people in it, working on things like risk analysis, the role of electrification in economic growth, the basic technologies of nuclear power and how they might trend in the future and so on. And so I'm still having fun.
So that sounds like a wonderful arrangement.
Yeah, yeah.
Well, Chauncey, this certainly has given us a wonderful overview of a very productive career, and it encompasses so much of the whole field of not only nuclear energy, but energy in general. And I think this is a very fine, comprehensive exposition of your own personal experiences tied together with the whole energy industry.
Right.
And I want to thank you very much for your contribution
you're very
here.
You're very welcome.
And we'll just hope that we're able to get some duplicates, which I will send you as soon as we get